So we have an understanding of I/O, okay, from an implementation point of view. Now, what does I/O have to do with inter-process communication? Okay. So let's try to answer that question. Okay. So we want, pictures like this, whatever they mean. Processes talking to each other, sending information to each other. Okay. And I've gone and put this console API here. Somehow that's relevant to inter-process communication. So those of you especially who've done the networking course, maybe others too, can you try to bridge the gap between IPC and I/O?
One process is going to be the producer, and then put it into the communal process, and then maybe the consumer can consume whatever.
So what is IPC? And IPC is the producer-consumer problem. It just so happens that the buffer is distributed. That buffer was all confined to one kernel space. Now the buffer, it just happens to be involving two parties, right? So if you want to write some data that another process is to consume, you're writing into some kind of bounded buffer that the other process can read. And if you're if you're getting information, you're getting information that some other process has written it. So from an API point of view, we are again doing puts and gets, assuming we're happy with character I/O right now. Okay, we go to non-character I/O later. So at an abstract level, that's what we're doing. But I've got multiple processes. Each process, we're assuming that the processes don't share any objects. When we had multiple threads in a process, we assumed there was a particular buffer object that was shared by both threads. And each thread went and said, invoked the get and put on the same object. Now I am in two different processes with different objects, different JVMs, different address spaces, no sharing of objects. So conceptually, logically, I'm putting it into a distributed buffer. What does that really mean? I mean, what are the specific objects that the two processes are dealing with to make this happen?
Some like shared memory space.
Sorry? So we have no shared memory space. That's what we're assuming. One's in China working on the computer, one's here, and we're not trying to simulate one big memory there. Yet we are able to send messages to each other, and conceptually we are sending messages to a producer-consumer. So what happens? You networking guys, you should be able to answer this. What are we really doing?
Message passing.
I know, but message passing means what? Message passing is really having a distributed buffer, bounded buffer. How do we go and simulate a distributed bounded buffer using some abstractions? So how did your mail client send information to a mail server? Those of you who did the course on writing mail servers and clients. Yeah.
Can you just send it as this to a port?
You sent it to a port. So the client did what? It said send to a port object, and the server said what?
It will send on a port.
So, but these are two. They were not the same port objects, right? I mean, they're in different address spaces. So how were they connected to each other then? Okay, so you actually wrote to a socket object rather than a port object, and you read from a socket object. And how did the socket objects get paired up?
It's kind of like a finite state machine. So one would be emitting characters, the other one would keep track of whether it was following the procedure correctly or not. And it would update based on what it's used.
Okay, so you had some kind of, you made sure that you got what you expected. Okay, that's sort of a protocol level thing. But how did the client object process wrote to something in its memory, right? There was a socket object in its address space it wrote to. The server object read from some socket object, the server process. And somehow what the client sent got received by the server, even though they were invoking operations on their own local objects. How did the connection? I understand that you want to only do something that was expected. I wonder if I talk too long without doing anything. Okay. How did these two socket objects get paired up somehow?
So you had one socket on the side that was the server, and it was listening for incoming TCP connections and wanted to initiate a connection and would allocate a socket for you to communicate on that sort of data channel. So you could communicate to a client and server on that fixed channel.
So there was some complex stuff going on here. That there was an object that the process wrote to. There was another object that another process read from. And then there was yet another object that somehow made that connection happen. Okay? Okay. So let's go slowly here. We'll have a process that has not a console object, but we'll call it channel. Okay, because it's not quite reading and writing from the keyboard. So each process has a channel object from which into which it can put characters and from which it can consume characters. Okay? And now the question is, well, this channel object only this process can access, so there must be another channel object at the other process on which you can also invoke get input, because we want duplex communication. We want information to be written and read along the same channel. Okay? So those are your two sockets, but I'll just be more abstract and call them channels right now. Okay? So we have two channel objects that behave like our console object. They have gets input, the same interface, different implementation. Okay? The interface is get input. This happens to be a channel implementation of the interface rather than a console implementation. Okay? Somehow they got paired. Okay? And what really happens is that when you put a character in your object, that results in the get on the paired object returning that value. Okay, now your put is affecting another get. Before it was the keyboard thing, now it is two processes, and my put affects your get and vice versa. Okay, so somehow when you put there, the get gets consumed. So that's the interface. That's the magic. If you can somehow get these paired up, it'll work. Okay, and the question then becomes, how do these two guys get paired up? Okay, how do they magically get connected to each other? So before we get to that, let's try to answer another question. I might have more than one process talking to another process. Okay, so I might have if I put another process into this picture, do they all share the same bounded buffer? No. Why not? I kind of gave the answer before that, but so it might not be, some messages might be meant for you and it's not clear. So you're going and making a transaction on Amazon and I'm a client and there's another server and somebody else gets the result back, right? You don't want that to happen. Okay, does not allow private information of credit card and other information, and it just doesn't make sense in many applications. Okay, we'll see later abstractions where you do share. Okay, so what's really happening is that you have, if you have a process that's talking to multiple processes, you have a process on the right that's talking to two left processes, they all get their own private channels. Okay, so each of them has got a separate bounded buffer. So now the question is, how did this pairing occur? Okay, and we got the answer. Yeah.
Isn't it like a selector that picks the channels and assigns it?
You're saying there's some kind of selector.
Yeah, like a selector object. That's what the NIO would say.
Okay, so you're saying in NIO there's a selector object and maybe that makes it happen?
Yeah.
Not quite. The selector object is the most important object in NIO. So So don't give up on that object. We're going to understand that better. But what he said about there being another object, you're right. You guys are right. That there's another object that does it. These two objects on their own can't get paired up. We need another object, whether it's called a selector object. What did you call it?
It was kind of was it not a channel just waiting for incoming TCP connections?
So it's another kind of channel you can imagine. Okay, selector is something that chooses among messages that have come in. That is yet another kind of channel. Okay, yeah.
It's like a TCP handshake, like before.
So yes, at some point there's yes, underneath there's some kind of handshake to make a connection happen. So underneath that's what's happening in the networking level.
Was it like a socket channel in NIO?
Okay, so in NIO it's called it's another object. Whether we call it selector or socket channel, it's actually called server socket channel.
Servers.
Okay, so server socket channel. Okay, so I've got 5 minutes left. Do you guys want to take 5 minutes to write your diaries, or do you want me to continue on? Let's take two more minutes since we're on this thing and think a little bit more, and then I'll give you 3 minutes there. Okay. So, channel creation and connection. How does that happen? I'll review this again next time. So, why is this now a problem? Why was this problem not there when we're talking of console? Okay. When we're talking of consoles, there's only one console object. Each process has a standard input and output, and I've combined that into one. So there was no magic about how that object got created. That object was there. Okay. One of the problems we are facing, and we don't quite know the answer, except you do, okay, or at least you've articulated it, is because we've got to create these objects dynamically. Okay, because for each connection, if I'm a process that talks to 10 other processes, I need to create 10 objects dynamically. Okay, and each process doesn't start communicating. It may or may not decide to talk to me. So these objects have to be created dynamically. Whereas with the console, it was done just done automatically. Now forget about IPC. Do you know of another way to create such console-like objects in your process, even if you're not doing distributed computing dynamically? So we have standard input and output. We are born with that. Are there other objects that we also read and write to that are created dynamically?
Yes.
Files. Okay. So in Unix they say everything is a file, by which they mean that this put and get interface applies to many kinds of objects. Okay. So the key is to use principles that we've learned from creating file objects to create these communication channel objects. Okay. So now I'll stop at this point. You've got 2 minutes, and we'll start off from here next time. Okay. Yeah.
Can you go back to the format for the
Diary.
diary?
Okay. Okay. Just write it down on a piece of text right now, and I'll post the format on Piazza. Okay. Anything else? So how did we get to all these background concepts? I started using words like intra-processing and threads, which you guys didn't quite understand, and a bunch of you told me that I needed to clarify. So, but the basic plan we had here was that we'll talk of we're going to talk of NIO, and let's do it from first principles. So we'll talk about what IO really means, so that there's no mysteries there, and that's where we went off and talked about interrupts and so forth. And then we'll talk about what what inter-process communication means as IO. Okay, so how we can go from IO to inter-process communication, which is the foundation, which is what distributed computing is. And then we'll look at the non-blocking aspect of inter-process communication. Okay, so that's how we went. And IO is something you've done, in CS1, CS2 kind of classes, but you didn't quite know what's going on underneath. IPC is something those of you who've done networking have used, but maybe you don't quite know what's going on underneath, or at least don't understand the blocking aspects of it, which you need to understand to do non-blocking. Okay, so we talked about I/O as through the implementation, and we saw that when you write something, you're writing to a buffer that is being consumed by a device, and you need synchronization, and the output interrupt device will always go and interrupt after it has finished an operation, to say I'm ready for more. So when there are no more operations to do, interrupts are disabled. Okay, it doesn't wait; it just disables interrupts, and the producer, every time it goes and puts into a empty buffer something, it goes and enables interrupts that causes the interrupt to be posted, and the cycle of processing interrupt to start. Okay, so that's the part that we talked about in the background material. Okay, and this is basically a form of signaling that works for devices. And we saw then similarly input also involves a producer-consumer problem, but the dual of the previous problem. So now the producer is the application code is a consumer, and the device is the producer. And again, just like the selector thread in NIO, the interrupt routine can't block. And here we can't do any tricks here. The producer has to be somehow slowed down. And the way it's done, for instance, with the keyboard, is that if the user types ahead a lot, you just get a bell saying, hey, the program is not ready to process. Okay. So that was I/O, and we saw this earlier. Then we started off looking at the second part, and we said, well, we have this interface console with put and get. It's a nice interface. It seems to suffice for also multi-process communication, because what are you doing? You're transferring information to another process or receiving information from another process. So the get and put interface seems to work. We just need a different implementation, and it won't be console. And also what we need to do is we need to have two processes involved there. When we had two threads, we could deal with one object because the threads are guaranteed to have a common address space. With different processes, we are not assuming shared memory, so we need to have not one object but two objects. Okay? So we'll call such an object a channel or a port. Okay? Channel to be consistent with what NIO calls it, port to be consistent with the terminology I'll use later. Okay? And we get and put to it, and when there are two processes that are exchanging information, there are two such objects. There are endpoints. This channel the objects are endpoints to a conceptual channel, and the put in one influences the get in the other, and vice versa. Okay, that's what we saw. Then the question became that a process can talk to multiple processes. So if there's a process A that talks to process B and C, then should all processes B and C and D that talk to A share a common logical stream of information? Okay, if that's the only two choices you have, you can either have complete sharing or none at all. And we saw that we probably want separate channels because I don't want my bank balance to go to you, and we might be talking to a common server that services both of us. Okay, so we saw that this is all review. I'm just sort of reminding you what we did earlier. Okay. And so we have a process can have multiple channels that are used to talk to multiple communicating parties. Okay. So we can talk about the blocking semantics of put and get, and we'll do that. But before we talk about that, there's a more fundamental sort of naming issue. How did two processes that are talking through a producer-consumer bounded buffer that's sort of distributed here, how did their two channel objects get connected to each other? How are we making sure that the put in the top one put is going to the upper get, and the bottom put from this big process is going to the process consuming from the bottom get? Somehow these got bound. Okay, and we can try to go and ask the same question for IO creation. I should have had console here. How did we go and get the console object? Okay, how did a process get hold of a console object? And those of you who've seen operating systems, or if you even looked at Java, in Java you say system.in or system.out, somehow magically there is a singleton that you interact with. See how important singletons are? Okay, And those of you who've done operating systems, you've seen this notion of standard input and standard output. Okay, underneath that's just file descriptors that are bound. Okay, so that's not a problem. When there's a singleton, you just somebody magically you get it. Okay, and then when do we have this kind of buffer which you can put and get this file object, essentially file interface? You know, are there examples of classes that have multiple instances of this? Okay, and we saw that too, that we can think of this as being an IO stream object. That's the interface or the abstract class, if you will, and then console was a subclass of it, and the file stream is another subclass of it. So in operating systems in Unix, people say everything is a file, and that's kind of silly, you know. I mean, a file is a file and a device is a file. How can, I mean, why do we have two different words for file and device if they're the same thing? What they really mean is that a device also implements the file interface, even though what it does is, in the implementation wise, very different from what the network device would do or some other object that has the same interface would do. Okay, so we really have file streams, and now let's go in. I think we might not have covered this. So how do you create file streams, given that there's more than one file stream that you can have in a process? In OS terms, creating a file stream means what? Are you creating a file? What are you doing to the file? Making a pointer to the file. What's the term used in Unix for that? Your descriptor. So when you, what operation gives you a descriptor from a file? You open the file. Okay. So again, this is not Java. Okay, this is abstract. You can imagine a file factory. That's not how Java does it. Do a new file, which has a method called open, that given a string will return to you an instance of this particular class. Okay, which will be an IO stream. So you have to do something. So there is an external name. The reason, when I say external name, what does that mean to you intuitively or technically? Yeah, right.
Some like unique ID.
A unique ID, unique to what? Unique to what set of things?
Unique to a particular file or type of file, perhaps.
Yeah, but it's external. What do you mean by external? Why did I use the word external? There's internal names and external names that a program refers to.
It's fixed beyond your control, kind of.
Beyond your control, okay. Yeah.
I was going to say external, like maybe like human readable, so like.
It's human readable, so it's not a pointer. It's a name that is not the name of some variable internal to you. It's a name that can be shared among multiple processes. That's going to be key here. Okay? So it's a name that is not bound to a particular process, so the process can write to a file and later read from it, and that's a different process. Or two different processes running concurrently can access the same file. It's not a name like the variable I inside a process, inside a program. Okay? So a particular process can talk to multiple file stream objects, and we do this through the open call. Okay. So we've got some grounding on how to get multiple instances of this IO stream object that we're very interested in. Okay. And important thing is the open always is associated with some access. So you open something for reading, writing, or reading and writing, and the open may fail. In fact, open is a very important call from access rights point of view, performance point of view. We don't want to check every read you do for read access to the file. So what you do is you go in at open time, go and say I want read access. It'll check whether you have read access or not, and then it won't check every read operation. Okay, so this is an extremely important thing for performance. Okay, and access rights is going to be important because we have multiple processes running. So let me now ask you a sort of trick question, a little bit of a trick question, or a very straightforward question. So the model seems to be that we needed some access control even for inter-process communication. Some arbitrary process shouldn't be able to come and talk to another process. Okay? And that seems to mean that we should have both processes. So how do we make sure that two processes can't just start, some arbitrary process can't just start talking to me if I'm a protected process? How do we make sure of that? I mean, there's access rights in a file. Access rights are always relevant to a particular operating system. Here I might have something running on Google's operating system and something running on UNC's operating system. And how does the Google operating system make sure that arbitrary processes don't start talking to it?
They have to like identify it some way.
So somehow the Google process has to have control over who's talking to it. That seems like an obvious thing. But have you seen any kind of inter-process communication where the processes don't even know who they're talking to? We just get connected magically. I know, but so that's conceptually a bounded buffer. That's very good. Conceptually that exists, but in reality, have you seen in any system a bounded buffer that allows multiple processes to talk to each other, and the processes don't even know that they're talking to each other? And this kind of not knowing is considered a very good thing. You've all seen it. Anybody who's done shell programming has seen it. Probably, depending on what commands you use in shell programming. What's the most fun command in shell programming that allows you to really program it? As a user, you can program. So Unix versus Multics, you OS guys. Unix said we'll try to do few things, okay, and Multics said we'll do everything. What was it that in Unix that gave it the power of Multics essentially? Pipes. I got the answer I was looking for. That you write small programs that do one thing right. Each one of them does one thing right, and you compose them to create multiple things. There's many reasons why Multics was called Multics. It did everything. From a teacher's point of view, you love that operating system because every concept that's been invented, it implemented, almost. Okay, but the one thing that in Unix there was a big principle was that we compose things. So pipes, what happens? You don't know. The process doesn't even know it's writing to the standard input. It's getting from a file. It's getting from another process. But it's all within a particular operating system. It's all for the same user. So we don't have to worry about access control. We have to worry about access control when we're talking about multiple operating systems, different machines, different users. So you need to be able to, both processes have to connect their channel objects. We can't just have these channel objects connected unilaterally by some external agent, which is exactly what happens in pipes. Okay? We want them to be connected explicitly, so each one of them should have some control. So we'll need operations at both ends to be performed before you've agreed. It's like when you become a friend in Facebook, you have to both agree. Whereas in Twitter, I guess, one party can just decide to become a friend. So that's sort of the difference. Okay. So that seems to indicate that there has to be some awareness of the party you're talking to. Okay. Pipes are all about not having awareness. Okay, so that you have transparency and you can switch things. Now we need awareness because we have access control. Okay, so does each process have to know about the other? They both have to do something to connect, agreed. But does each process have to know something about the other? Or should it? I mean, when I say does it, you have to reason it out because you may or may not know the answer.
Depends on what you're implementing.
Okay, so can you give me an example where each process should not have to know about the other?
You're querying like an API for some data or something, and you need to establish the connection and maybe some processing down there and to send you the response.
Okay, so the
You
process
don't know what's
A.
doing behind the scenes.
Okay, so awareness is a term we use in software engineering a lot. That I am not aware of what my observer is doing, I just call the notify method. Okay, I'm not aware of what the object, command object is doing. I just call execute. So I agree that that level, you know, for that purpose, you just used an API rather than knowing the implementation of the API. Use an interface. You don't even know what class implements the interface. But I got that. Now I have two processes, A and B, that have to talk to each other. Somehow the connection has to be established. Okay. And the question is, you know, how did the connection get established? Process A could have talked to process B or C or D, and there were choices to be made, and how much choice is involved, and does each, if A and B need to talk to each other, does A have to know something about B and B have to know something about A to even establish connection? So I'm talking port is some feature of a process. Before we go to port, let's go and talk about, do I have to know, or in your language, you have to know about ports of each process. Does A have to know about the port of B and B have to know about the port of A, or is one level enough? We know that it can't be that both don't know about each other. That's what happens in pipes. And we know we don't want to do that. So somehow a choice has to be made, and the choice, and the question is, do both parties make a choice, or only one party makes a choice? Yeah.
Would it be one party knows of the other, and so like a client would know that a server exists and will like request a connection to that server. But like the server doesn't need to necessarily know that that client exists at all.
So one process can be written to be oblivious to other processes. Okay. In some cases, we might need to have both sides now. But when you talk of server-client computing, that's exactly what we're talking about. What is a server? Provide some service. No, that's not quite what it is. Technically, a server is the one that doesn't know about the client, other parties. Server is the one with a known location, with a known port as we see it, and it can service a large variety of clients, and then it can check whether a certain client, you know, which tries to connect to it, satisfies certain access control properties, but it doesn't have to know the identity of them. Okay. So if we did that, it would not allow servers to communicate with unknown clients with unknown properties. So one process client knows about the other, and the one that's known is called the server, and the one that's unknown is called the client. Okay, even though intuitively the one that's known is providing some service, but you know, we'll see examples where that's not necessarily the case. So now my question becomes, what do you know about the other process? Do you know the process ID? And if not, why not? So should I know the process ID of the process that's serving my Gmail requests?
This kind of goes back to what you were saying about ports. We don't, like, the whole idea of ports, we don't need to know the process ID. We expose this port.
So why do we use ports rather than process IDs?
Process IDs can change.
Process IDs can change. It's a very simple question. It's not as if the Gmail server will never die once it starts, right? I don't want to be, you shouldn't have to go and broadcast to everybody, okay, the new process ID is this one. Okay, so it's like, how did we guys end up in this class? Okay, the classroom was a port. I knew to come here, you guys knew to come here, and so there's a level of interaction there. Okay, so process is local to OS and changes each time the server starts. Okay, the process ID makes no sense outside. So just like the variable I in my address space makes no sense to some other process, but a file name does. In fact, originally when sockets were created, they used, rather than port numbers, they used file names. Okay, you can still do that, by the way. Huh? And you can still get sockets from file names. So the client knows the host and port number of server channel. Okay, I mean, this is obvious, maybe because we use it, but this is the reason for it. And pipes came first, sockets came later. So I'm showing you the history of how people thought. Okay, so first interprocess communication was done through pipes. That was the only interprocess communication. and then sockets came around. I mean, between the time pipes were created and sockets came around, there was a lot of research all over the world in distributed computing on what kind of IPC mechanism to have. And then sockets came from Berkeley, and all that research just died. Okay, so and now sockets are considered just standard, and it's amazing. This was mid-80s. So many years later, we still have sockets. So there's something right there, even though all the research groups that, and I was in one of those research groups that saw sockets said, "Oh, we are doing much better. Our abstractions are much better." And sockets were confusing, and we see why they're confusing, because they try to do many things. But they've stood the test of time. Okay. So now the question becomes, now that we know that there are multiple private channels for different clients, does each client have a separate port number? No. Why not? So you're saying, having seen, so you just know that. But can you defend that? Why shouldn't we have a port number per client? Yeah. So that's the thing. We come back to the same problem. Or we would have a finite number of clients. So the server would, yeah, because exactly, the server wouldn't know which port to listen on. Okay. So even though we have private channel, this is where sockets get confusing. Okay. This is what nobody else had done before, Unix sockets, where everybody before had gone and said either we have shared channels, or if you have separate channels, then we have separate names. Nobody has said, oh, we'll have one name for multiple channels. And that's why sockets are so confusing too, even till today. Okay. So we have one port number, but multiple channels. How does that happen? I guess it's also telling me that you guys should. Okay. I want to give, okay, let's just take a minute. So, does the server have a separate port number for each client? Cannot support an arbitrary number of clients and implies client awareness. Okay, so that's kind of what you said. Okay. So how do we have this magic that we have private channels but a common port number? Those of you who've done networking, more of you can answer that question. How is it that one port number can yield multiple channels? Yeah. Each client will have its own. Each client does have its unique address, good. But how did so that's true. So the endpoint is unique, that's half the answer. But how did we go from a common port number to separate channels? So
don't you find like a socket for each connection?
okay.
Like you're creating a unique socket for each client server.
So if you think of them as, so that's what we have. We have a socket endpoint here, a socket there. They talk to each other, right? Private connection, good. They use a common port number. So is there any new abstraction we need besides this? You're right, underneath, because we have separate addresses for clients, we can create this. But do I need some other abstraction besides the abstraction I've shown here to go from a single port number to multiple private channels? Selector is something in NIO. It's not quite, but
or
maybe.
Just the generalized principle of something that manages receives the incoming connection, and then some object that manages creating the channel object and associating it with the unique host ID.
So what you're saying is we need another abstraction,
Yeah.
not the channel abstraction. We can call it selector. We can call it a factory. Okay, that will go and list that, to which you can send messages. And that will go and then create a separate private channel. So we need indirection again. Okay, so there is, to connect, we need to connect so that we can send messages on a private channel, we need to send a message to another kind of public channel, and that channel will give you the private channel. Okay, so let me stop at this point. Okay. So we've been looking at NIO, and we saw that we need some communication medium between two communicating processes, some abstraction, on which you can invoke methods to send messages and receive messages. Since we're talking of multiple processes, we need to have different data structures that are not shared through memory, shared memory, in different processes. So what is this object on which with which we interact to send messages? Okay, so that object we called a channel or a port. The interface of that object is very similar to the interface of the console object. Okay, and we call it an IO stream object. So that's the interface. The implementations are different. And since we know how the console works, we just have to understand how this abstraction differs from console. Okay, so the interface is the same. What about the implementation? And there are many aspects of the implementation that are important. And one of them is that we might have one process talking to multiple channels. Okay, so we have on the right a server that's talking to multiple clients. So we want each channel or each communication to be private. So that server needs multiple instances of this object. Okay, so how to create, how to create multiple instances is what we looked at. And where were we after that? We saw that the idea of having multiple instances of that abstraction is not new. With files, we have the same idea, same notion. And what we do is, and also, okay, I guess we had gone through this whole thing, and we reached port numbers, okay, and we said that we need a port number, an external name that two processes can agree on that can connect their channel objects. Okay, in the case of file, that is a file name. In the case of channels, that is the host and port number. Okay, so the issue that we were looking at was that how do we create from a public port number that is known to multiple clients and a server multiple individual private channels. The port number is public, but the channels are different because they have private information. Okay, and that idea is not entirely new, because you can have one file name from which you can create multiple file stream objects. They all ultimately write to the same file. Okay, that's why we need some concurrency control. Things are going to go bad, but they are writing to different points in the file. I might be writing to position 1, somebody else might be writing to position 3, and so they are basically there is a notion of using one external name to create multiple objects. Okay, so what we'll do is, and this is where I sort of stopped, and I remember I asked the question and we didn't quite get to the answer. So what's the key here? It's not the same. It's not the same as the file situation. So what happens underneath to create from a public port number multiple channel objects that are, and what does it even mean logically for that to happen, that are associated with that one port number? So one port number, multiple channel objects. What does that mean, and how do we do it? Yeah.
So going back to the networking aspects, we have this accepting port that all the clients can connect to on the server. And what the server does is it creates, like you said, it will say, okay, the process that just came in, it's going to be bound to this other process on my side, and it'll, right, and we create that separate channel. So you're not actually communicating necessarily on that port number. That's simply where you connect to, and then the server-side process will do the actual binding to some hidden port number.
Okay, so the answer to most computer science problems is indirection, right? So what we do is, yes, we'll ultimately be creating multiple private channels, but we will create one shared channel associated with that port number. And that shared channel will then, communication with that shared channel will result in the private channels being created. Okay? It's like you're going to a restaurant and you want your separate tables with your separate servers, but you have to line up to get a ticket or get a table number. Okay? So there's somebody who's dispatching you, and you go to the restaurant and you know that particular name. You go to that name or name, and then you get the private channels. So that's the key. That there is a shared port, there's a shared channel, but that shared channel is not meant for sending normal data messages. It's meant for creating shared channels. It's like saying, can you guys see an analogy with the factory idea? So a factory is, how would you define a factory object? Create new objects. So it's just a way of creating, but in its own right, it's not interesting. It's interesting because it creates another object. So this is, you can think of this as a factory object. Okay? It's listening to messages. So a lot of people call it a listening port. Okay? So here's the deal. We will have, so your endpoint, the client's endpoint is connected at different times to two different objects. The client endpoint is either in a connected state or a not connected state. When it is in a connected state, you can do gets inputs. When it's not in a connected state, what can you do it? What can you do to it?
Wait for it to be connected.
So how do you wait for it to be connected? You have to somebody has to initiate it. The connection between a client and a server is initiated with the client or the server. So the object on the client
Sends its request.
So you have to, as a client, you have to go and invoke a connect operation. So we have not only the put and get operation that we had on the keyboard, but now I've got another operation called the connect, which goes and says, put me in line to get my table. Okay? And that will send a message. So at the server side, the server is going to have two different objects. The client has one object that's connected to either one server object or another server object. Okay? The server begins with a port, a channel that is associated with the port, and it goes and this is sort of, it goes and asks a factory object, a pure factory object, to create that port. So it goes and says, give me a server channel factory. Give me a server channel factory, we'll call it. So it uses a factory object to create a factory channel. Okay, I'm using factory in two different ways. Okay, so somehow it gets an instance of this server channel factory, which has got an accept method. Not a read, not a write, an accept method. Right? And that connect on there is going to send a message that is relevant to the accept method. Okay? Once they're connected, we'll get some object at the server end that is created to match the channel object on the client. Okay? But until that happens, until the accept happens, we don't have it. So now that we have this connect and accept, somebody want to define what connect and accept do exactly? So connect sends a message to the server. What happens when the message reaches the server? Exactly. Where does accept come in? He said until it's accepted. What does that mean?
Once the new channel's been created.
So, okay.
Doesn't the new channel that gets created become the server has to respond with that information? Because the channel is connected now?
So that's right. So the connect message, when it has reached the server, it has to get accepted. I want to understand what accepted means. So let's go and see. The accept method is called by the server, or it is called by the system underneath automatically. The server created the server channel factory object. That it did. That did not get automatically created. Did it call the accept method? Should it? If it should, what would that mean? If it shouldn't, why have an accept method? Yeah.
I think that it doesn't, because the client's connect method should interact with the accept method, and if it didn't have, if the server were calling the accept method, then it would need to have some sort of a listener for the, or it would need to have some other way of interacting with the connect method.
Okay, so you're saying if the server had to call the accept method, that would create problems. And the problems would be?
That it would need to be like listening for the client, or somehow it would need some other way of knowing that the client is calling the connect method, which is the entire code.
So you're right. The server does need to know that the client called the connect. Okay, let's I'm not, are you right? So should the server know that the client sent a connect message? And should the server have the ability to not be connected? You're saying yes.
Yeah.
Flexibility is good. So server should have the ability to go and say, I'm not in a listening mode right now, or I don't want to listen to this particular client. Okay? Given that as a goal, should accept method be, should the channel be automatically acceptable, or should the server call the accept method to make it acceptable? Should. So you give this right reason but the wrong wrong way you went. So the server calls accept to say, I am willing to listen to one more connection. After 2 accepts, it might say, I'm not listening to anymore. I'm overloaded. That's it. So, or it can say, I'm not listening at all. So that is why you have a connect method of the client that says, I want to connect. Just because you created a socket channel doesn't mean it's automatically connected, because you don't, when you created a socket channel, you never specify the port anyway. So the connect method will say which host and which port. Okay? In the case of accept, the port number is implied. So we could have the accept be automatic. But but just remember, access control is a big deal, and we want access control. And access control means that both parties should decide they want to talk. It's not like the pipe situation we talked about earlier, where the 2 processes didn't even know they were talking to each other, but they got connected. No, now we're talking of one computer being at Google, one computer being here, and we are trying to, put Google down perhaps, because there's a hacker here. So we want all kinds of controls. So accept method has to be called explicitly to say, I am acceptable for the next message. After each, so now let's go and talk about it. Supposing the client calls connect and the server never called accept, what should happen? The message will go to the server, and what happens to the message? It's just dropped or waiting, Right. Supposing the server calls accept and there's a pending connect, what should happen? That should be accepted.
Verifies that it's willing to accept.
It can verify that, and it can just accept it. Okay. Assuming the pending connect. Actually, I'm not quite sure what happens with the blocking operations, whether it will actually honor a connect, a pending connect or not. But I would say yes, because it shouldn't depend too much on timing. On the other hand, the client should have known that the server exists. But what if the server is in some state where it just wasn't ready to do the accept at that point? So I would say there's a pending connect, it should, and it hasn't timed out, it should be honored. Okay. And if an accept occurs and there's no pending connect, what should happen?
Just continues.
Should wait till the next connect. And the connect call itself waits until it receives a message from the server saying that accept has occurred. In the blocking semantics. In the non-blocking semantics, who knows what's going to happen? Okay? Yeah.
So, I'm confused about, if you just want to connect to, one client and then have your server stop listening. You said when we call accept, that means that you're listening for more clients?
So you're listening for the one more.
So how do you accept just one?
You're starting at 0, then you call accept, first one comes in, accept, and then you go to the state.
Oh, okay, so you
Then
started,
goes-
you started accept.
And then you loop again. And then you loop again and do accept again.
Okay,
Accept occurs in a loop.
okay.
Okay? So let's look at this picture. There's a lot of animation here. These slides take forever, guys, to make. And you will see why. Okay? So the server went and created this. The server then doesn't accept. Okay? So the red line means it instantiated. The blue line means it made a call. The client made a connect call. This is the sort of sequence we had. That sends a message to the correspond that's matched with the corresponding accept. Okay? This new channel object got created at this point. Right? That's a side effect of the matching. That's what you guys were saying all the time. Okay? A message goes back to the original client, which unblocks. Okay? Now they can do a matching put and get. Okay? Second client, you do another accept. Okay? And this guy does a connect. Message goes, and there. Okay? So you do as many accepts as you want to accept. Yeah.
So is it just a new channel or a new port?
The port number remains the same.
Okay.
You're going to the same restaurant. A new client's come in.
But like each unique channel is still on the same port.
It's still so. The tables we got were in the same restaurant.
Okay.
So we're getting the same kind of service. Think of it that way. But there's still one usher so far. Okay? Questions? Yeah.
I thought when we learned in Internet Protocols and what
You learned in where?
Internet Protocols,
Yeah.
networking course, that like it listens on one port and then once it creates a connection, it moves that private channel to like a different port.
But it's like it's not like
That's like
it's not a
what
work to
TCP
it.
connection.
It's kind of it's just some like binding that process that channel.
Okay. So here's the deal. Somewhere when I'm sending messages from this process to that process, I have to somehow address that other endpoint, right? That's an implementation detail. Okay? And internally, there can be a little dynamic port created that has got an internal name that you, as a programmer, didn't have to worry about. Okay? It's like when I open a file with a public name, imagine each of us that opens the same file gets an internal temporary file. And one of these temporary files will win, assuming that doesn't quite happen. Okay, but we do get a little buffer. So imagine that. But that port number, if it is totally not visible at the API level. Okay, that's visible at the protocol level. So there's many things that can happen. The client can go and send its ID. When the client, we don't know how it's implemented underneath. When the client created this particular socket, it can create a little port number saying this is my port number for my internal ID for this public port of yours. And every time it sends a message from put and get, it can send its number. At the server, there can be a table that goes and says, aha, given this public port number and given your private number, I can go and map this to this particular channel object. Because somehow that channel object has to be addressed. Because it's receiving messages from multiple places. Okay? How that's done, I don't know. I think they're both plausible implementations, where in one case, the connect message gets an ID that the server uses when the message comes out, or when you just do a connect, it sends an ID. It can happen both ways. Okay? But the public port number, the port number you have to reserve, is only one. Okay? Questions? So server accepted a loop with each accept returning a new connected channel in the blocking semantics. Okay. Now let's talk about ports. As you hinted, we can have multiple internal ports perhaps for each server. Does it make sense to have multiple public ports? In other words, does it make sense for one process to have multiple port numbers? Or is the port just a public name for a process? Yeah.
I guess if you wanted to have part of your website or whatever this is, give access to certain people or certain things, if you wanted to divide that up.
So supposing you want your website to offer two kinds of services, one service to a particular set of users, another service to another set of users. Yeah.
What about like load balancing? Is that an issue?
So load balancing, that could be a reason for that, but load balancing you would need even if you have one port number, right? If you have one port, you're a web server and you've got 1,000 people, 10, you still need to do load balancing. And you probably need some other mechanism for load balancing than just port numbers. Okay. In the restaurant analogy, does it make sense for the restaurant to have two different sets of dispatchers? Does it make sense to queue up at two different places in a restaurant based on what service you want? No?
It's like a VIP lounge or something. You could have like a second line stuff.
VIP lounge, or after the Super Bowl, won't you think a bar and a restaurant would be two different things? You know, you go to a restaurant, they say, oh, you can eat at the bar. So if you have multiple kinds of services, which is like what you just said, you know. So example server with multiple ports, and by the way, guys, if the grader works as we envision, from Eclipse, or at least from a website, you will choose the assignment. You will go and choose the course number and choose the assignment and just say send, and you will get back a itemized rubric with points given. Okay, so let's take this example as hopefully a real example, and see why we might have multiple ports. So as you saw, we had an item to choose the course number. So we might have, that means, two sets of grading services going to the same grading server. So the grading server could imagine having a COM401 grader and a COM533 grader and a COM410 grader. And for load balancing and other reasons, you might want to have in the server multiple processes that do the work. Okay, that's often how load balancing occurs. That you can put the work on a separate thread and hope you have enough cores or processors, or you can put it on a separate computer. Okay, and what we do is we put it in a different process, and we hope that the operating system will do the scheduling on different processors. Okay, so now this dispatching server is talking to two sets of processes, the clients and the graders. And it is a fixed point. Whenever the grader comes up, it knows the dispatching server to go to. Whenever a client comes up, it knows the dispatching server to go to. It is the server, even though honestly speaking, the grading service is being provided by the grader clients. Okay, right? Because that's a service. They are the ones that are providing service. So because it's a fixed point, we call it the server, even though because it's a fixed point. So remember, server is a fixed point. Doesn't mean it's a server. It's really providing a service. So now the graders are being, not every process can just declare itself to be a grader. You shouldn't be able to just go and say, I'm the COM533 grader. And then I'll go and just see who's grading, whose assignment it is, and give appropriate points. No, there's security problem there. So we allow the graders must run on the UNC network, in the computer science department, and maybe on the same host. We can put all kinds of requirements there, whereas the clients we can be more relaxed with. Okay, so here's a case where the dispatching server is talking to two different kinds of processes, doing different things for different processes. In one case, giving a drink; one case, giving a restaurant, giving a regular meal. So a port is really a type of service, and one process can give multiple types of services. It's not common, but it's possible. Okay, so that's what a port is. And we're going to take this example to illustrate a lot of concepts in the future. Okay, so guys at least understand what the structure is. Okay, client goes and sends a request to dispatching server. Dispatching server says 401. Then we go to the 401 grader, sends a message to the 401 grader. The 401 grader comes back with a result, goes and gives it back to the client. The client doesn't know whether there's two 401 graders or one 401 grader, whether there's a specialized grader or a generic grader. It doesn't, it's oblivious to that. Okay? Okay. So dispatching server has separate ports with different visibility for clients and graders. Okay, and it's providing different kinds of services. So the question is grader client or server? And I'm saying technically, based on it not being the fixed point, it is a client, but conceptually, logically, it's providing the service. Okay. Okay. So master dispatching server is fixed points, so slave graders are clients but provide the service. So there's a master-slave thing you'll learn a lot in distributed computing. And master-slave has to do with load balancing. And the master just gets this work and gives it to the slaves to actually do the work. Okay. Okay, so let's get this right. Connect host port will return when? When there's an accept response for the server. Okay. Underneath there's a socket there, that's what I'm saying, server socket. I should really say server channel. But when we are in the blocking semantics, we're actually talking of the channel being a socket. Okay. Accept will block until client sends the connect message. So in time, will the accept return first or the connect return first? Accept return first. We don't wait back for an acknowledgement from the client. We'll just be in an infinite acknowledgement sending cycle otherwise. Okay. Port will block until? This is a tricky question. Messages sent on the wire. So you said, here's my character. It has to be accepted first by the kernel. Then it has to go on the wire. Then it has to be accepted by the kernel on the other side. Then it has to be gotten. This is a big life cycle here. So we wait until it's on the wire. That sounds right. Or received. That's even more extreme. What about the least extreme? In the kernel. We've given it to somebody who's responsible. Now we can go to sleep. We can relax. That means our bounded buffer was not full. That's basically what it means. Okay, that's what happens in the keyboard put also. It doesn't mean that it's been put on the screen. It just means that the kernel had enough space to accommodate our request. It's taken our request. We can relax. Okay, that's what this put means in socket world. In other words, it will mean different things. Okay, so when we look at the various IPC mechanisms that are alternatives to this, we'll see that it has meant different things at different times. This is not what this will mean in RMI. In RMI, it will mean that it has been reached, it has gone all the way to the clients, to the server also. Or it has gone to the other end also. Just send messages.
How would it know, like, if you're like just sending a message that it reached?
So we go and send a message to it saying we get an acknowledgement back.
Oh, yeah.
That is when your atomic broadcast will get slow. Because we'll wait till that time. Okay? So block until char in system bounded buffer. And char get, this is the easiest operation. You block until you get a character. Okay? Okay. So that's the blocking semantics. Now what if I want to communicate multiple characters? Okay, this is so we're looking at single character. What if you want to go to multiple characters? And we can say, hey, you know, there's always this tension in system design between economy of concepts and power, lightweight and power. So, you know, people like Gary Bishop hate Java because, oh, I got to learn so much and I'm too old to study this stuff. Okay? Or whatever. I hate types. I don't know what the reason is. Okay? It's actually he hates types. Okay? So I was telling him, you hate Java. Do you know Java? I says, no. So that's what I said. So he didn't want to learn about Java. Okay? And, if you go to third world countries, they hate seatbelts. And to me, Java is seatbelts. If you're a good driver and you say, I don't need seatbelts, but my mind wanders at every slightest pretext. So I want the type checking as much as possible so that all my errors are sorted out at compile time. And, Gary is a smart guy, so he doesn't make mistakes, perhaps. So I'm honest, honestly, some people, they make fewer mistakes. So anyway, so there's always this thing that give us this nice skinny language, give us these 4 assembly language instructions, and we'll write our go-tos and we'll write our loops and for loops, and don't give us all these exception handling and generics and all the rules associated with it. So if we take that extreme, we can say, hey, the kernel just gave us get input. You want to send it an array of characters, build a library routine. Big deal. Just go and put in a loop. Why go and make your operating system fancier? Don't put anything you don't need to, just make the operating system clean. And I'm going to say that's not a good idea. I'm going to say that's going to reduce performance. Why?
Well, you have to receive an acknowledgement for every single character.
If you're going to do synchronous, you're going to receive an acknowledgement for each character. Excellent. What if I'm not doing synchronous? I didn't even mention what synchronous was. So far, I'm just using that term because I needed a term for that. But when you wait till the other end has received the message, it's called synchronous. You can be blocking without being synchronous. Blocking means you wait it. Synchronous means you wait it until a certain time, until that the receiver has received it. So what if you're doing a regular socket put where you just wait till it goes in the system buffer? That's all you're doing. You're not getting an acknowledgement, but it's slow because this goes back to all the stuff I did about basic concepts and operating systems and kernel. Sorry?
The less still has to go into a protected mode every time you put something into that buffer anyway. So you're still
You have to switch, you have to go and make a kernel call each time. Okay? Now there's a little interesting thing that you say that put it in the kernel. Now those of you who took Don Porter's class, anybody took Don Porter's class also? So he's building a library OS where he's taking things out of the OS and putting in the library. And there are certain reasons, especially when you're virtualizing, where it's okay to do this because the virtualization costs you so much anyway that the virtualization becomes cheaper because your operating system is skinnier. So this argument doesn't hold always, but at least when you're not virtualizing, imagine making a kernel call for each character. Imagine you're sending a lot of characters, so many kernel calls. Okay? So much so that people have talked about putting your own user code into the kernel, user-defined code, which is very dangerous, so that you don't have to switch between the kernel and the okay? So kernel call for each put, which we don't want. Okay? Which means switch to kernel mode, context switch, and the kernel, what it says is, I got you captive. Let's go and just switch you to another process now. Okay? So it's just going to be slow. So nobody goes and just has a put character in their interface. Okay, this is just straw man. So now what we will do is we will change our put and get to be taking arrays rather than single characters or bytes. So now tell me what the write semantic should be. I'm sending a character array or a byte array. Okay, it's an array of some kind. Write will block until somebody raise your hand. You want to guess? Yeah.
The whole array gets put in the kernel?
Until the whole array gets put in the kernel. Anybody want to say he's wrong? So socket programming is very confusing because that's not what they do. What's the alternative to waiting till the whole array has been put? Write has a return value. One is to not block at all. One is to block until the whole array is put. What's an intermediate solution?
Block until it sends the first character.
Until it sends certain number of characters. Okay, however many. More than one character. More than 0 character. Okay. So if it can't send, so if it's as long as it sent one character, it'll unblock. It'll tell you how much it sent. And then you have to go in a loop and send the rest. Okay. So did you guys have to do this in your 431 assignment? You just hope that it'll all go across in one write?
Yeah. It was very like high level.
Did they tell you that it'll block till only a few, till you are not guaranteed? Didn't you look at the return value of write at all?
In Japanese classes.
Now, actually, this is what I know Unix did. At least Unix did at one time. Unless they've changed things in Java, I believe what the semantics I'm talking about, you're very good at looking at the web. Just at some point, look and tell me what the write does on the socket. And I believe it is at least one character goes across. And there was a book by Stevenson. Do you guys ever refer to that book? That taught you socket programming, how to use sockets. So they build sockets, and then it will tell you all the patterns. Then it will give you the loop to write, so that you can get the whole buffer set. Okay, so how much to block for? Write. Okay, tell me what the read should do. Logically, forget what Unix does or Java does.
Shouldn't it block until you receive the
So block until you receive the whole message. Now we're talking about stream communication. There is no concept of whole message. The idea is that you're just getting data incrementally.
You perceive like an end character and something indicator.
So remember, the reason why the reads and writes are confusing is because they're streams. And you're blocking till you've made progress, either in writing or reading. It's not a datagram. So the datagram is something you think of as a reliable, unreliable thing. But datagram is also a unit, a discrete unit. So stream communication and reliable communication go together. Datagram and unreliable go together, but there is such a thing as reliable datagram, which looks like an oxymoron, but really means reliable message chunks. Okay, so block until at least 1 byte in system buffer. Block until at least 1 byte received. And you guys didn't have to worry about this in your assignment, even though you're facing an even more confusing system, which is non-blocking. And that's because an IO manager is taking care of all of this for you. And when you say that the 700 messages got converted into 1,000 commands, that was not a statement I was saying. I was wondering whether it works right or not. So I'm glad it did get converted into 1,000 commands, because who knows what mistakes I might have made in doing this, but I had to do this stuff underneath it. Okay? And I didn't use Stephen's code, so I had to write my own code. Okay? He didn't do anything for NIO. Okay. So, question? Okay. Ooh, sorry, I got so caught up. Okay, guys, I've taken 2 extra minutes. Okay, so we were looking at blocking operations, and in particular we were looking at, what does it mean to do a blocking write or read, and this was unintuitive to you, that, so the question was how much to block for, and the write blocks until at least 1 byte in system buffer, and this is a stream communication, so you don't want to you want to keep making progress, and so it increases in concurrency. If you wait for all the bytes, then you'll have to wait a longer time. And read also is in the same spirit. You block until you get at least 1 byte. Okay. And you guys have found out that typically you will get the number of bytes you sent in the read, and typically you won't block after the write. Okay. You guys, in your networking course, did you write servers also, or just the client? Did you write? You wrote the mail server also?
Yeah.
Okay. So, so the moral of this is that, and I asked this a question, but it sort of is implied, that the byte buffer that is written may not be equal. So the buffer that I'm using byte buffer here, which we'll get to soon. But I moved some slides around, so things have become a little inconsistent. But imagine that you're sending not a byte buffer but an array, and the array you send may not be equal to the array you receive. Okay. So the message can be scattered or gathered. And have you guys? So you guys haven't heard the term from what I saw last time, scatter gather, before. So what would scatter mean intuitively? Become unordered. Yeah, you're gonna okay.
I was just going to say the same thing.
So the messages become unordered, meaning 2 messages sent in one order may be received in another order. That's one thing. What do you think?
Maybe the message is
Split. Okay. So when they get split, that's scattered, and if they are scattered, they must be gathered into a logical unit. Okay. So here you are. Here's an example of message scattering. The application told the channel, send me this message 1, and it gets sent as message 1 and then message 1 on the network. Okay, so the messages on the network are of finite size. What you can send can be very large. You can be sending an extremely large video or a very extremely large even text file. So you expect, that's something you've learned in networking, that messages can get packetized or split. Okay. So this means that the application gets these messages, and it must, in the application code, based on what I've told you about the channel, must gather these. Okay. So this is scattering and then gathering. Can you imagine messages getting gathered and then have to get scattered later by the application? That's kind of what you saw, right? You saw that there were fewer messages sent and more commands. Okay, so applications gather. So here the application sends message 1 and immediately sends message 2. Okay, maybe it sends 2 commands one after the other. And why would the network? So it goes and combines them into one message. Why would the network do that? Yeah.
If there are a bunch of messages, this can provide efficiency when sending across the channel.
So this is bulk transfer. If you write 2 bytes to a file, doesn't mean that every time it's going to go to the disk and write a byte. It's going to buffer them. It's going to wait for the block to be written, maybe multiple blocks to be written, so that the disk head is going to seek only once and not multiple times. So in general, bulk transfer is a great idea. Okay, and you still, again, you don't want to go and deal with multiple network interrupts. So you want to, if possible, send one packet. Okay, so it got gathered, which means that the application must go and scatter if necessary. And that is the behavior you saw, where there were 700 reads and 1,000 commands sent. That's what you told me. Okay. Okay. So how does application know how much was written in read then? The application said, I want to send so many bytes. okay, and what was sent may not be equal to, firstly, so there's many issues going on here. Actually, I'm combining them here. One is the system may not have the space to buffer them, and secondly, they get split. Okay, so the system doesn't have space to buffer all the bytes, and they will probably get split. Okay, some of it will go now, and some of it will go later. Okay, similarly, because messages might have got scattered, what you read may not in one read may not be what was sent. Okay, so how does the application know how much was written and read? And what's sort of the obvious answer? Yeah.
Doesn't.
Sorry?
It doesn't?
Okay, that's the really obvious one. It doesn't, and the system just takes care of it. So, but if it was so that's why I'm confusing two things here. One is scattering gathering, and one is how much was written to the buffer to the operating system. If not all of it was written to the operating system, the application must know that it has to go and issue the read again, write again. If not all of it was received in the read buffer, then the application must know that it has to issue the read again. Right? Because if you say read, if we say write buffer, and the system can only write 5 bytes, okay? System could do the following. It could say, okay, I could write only 5 bytes right now, but I'll write the rest later. You don't have to issue a write again. That's one semantics. What's the danger with that? Yeah.
You may depend on it being written, and if it hasn't been like asynchronously or something, your application will just break.
So you may depend on it. And why might you depend? What give me an example of something that you might do that would make things break.
You might like free it.
You might free it. You might rewrite it. Okay, so you might reuse the buffer for something else. So that's a danger. Similarly with read. You gave a buffer to read, only 5 bytes got read, and you can say, oh, the system will go and just fill the buffer later, but you might go and reuse the buffer. So since you have got unblocked, you're free to do something with that buffer. In particular, you can write that buffer. Okay, we're talking about blocking semantics. Okay, of course, there may be another thread that's also doing these things, so that can cause problem. So given that, and that's what is assumed here. The obvious way now to tell the application how much was written and read is to, maybe it's not so obvious. Sorry?
I was going to say send, have some sort of agreed upon format that says how much is to be sent.
So have some kind of?
Agreed upon, some sort of consensus on how you transmit, when you transmit, how much is going to be sent. So first you tell it how much information it's going to get, and then send the information.
Oh, so that's interesting also. Ask it.
Yeah.
So have two operations. One is how much can I send?
Or even if it's just the beginning of a sent, like a header information, how big the file is, how big the information is, the transmission.
So when you do go and do the write, what I had earlier was an array. You just sent an array, okay? And the array size, I assumed, was how much you want to send. So you said, okay, you could go and first figure out how much you can send and then send that much.
Yeah.
And of course, between that system call and the second system call, things might have changed. Okay, so what's the sort of, so you guys never looked at this, but what's the other, yeah?
Just return it.
Just return a value, right? So your read and write become functions rather than procedures, which is always little, it's a little confusing because there's a side effect now. Okay, these are functions with side effects. Okay, because they're returning values, so they're functions, but they do things, so they have side effects. Yeah.
Essentially, yeah, that's how the default. That's how the socket objects in Python actually work. They return how much was sent.
Yeah. That's exactly, and that's how it worked in your, yeah. And you guys just didn't look at the values; you just assumed everything was sent, but that's what you were supposed to look at. Okay. So return values. So how to reuse. So. So then the question becomes, so that's sort of the obvious answer, return values. Now what you might want to do is reuse your write buffer for multiple writes, and reuse your read buffer for multiple reads. Okay, so you gave a read buffer, you got 5 bytes. Okay, you learned that there were 5 bytes read. Now you're going to reissue the read request. You don't want to create a new array for that. You want to ideally give the same array back, but saying now read from, now write into it from position 5 onwards. Right? So the first time you said, hey system, write into it from position 0 onwards. Now you got 5 bytes. It filled up the 5 bytes. Okay, and now you're going to reissue the read, and you don't want to go and create a new array. Right? So how might you handle that? Yeah.
Don't you flip the buffer?
So you came a little late. We're just talking about bytes right now. So assuming you have only bytes, we can't do this. So now you use the word buffer. So bytes used as a buffer. Bytes, typically in C, an array is used as a buffer. So the array used for reading or writing is called a buffer. In Java, there's this notion of byte buffer. Okay, so somehow it's got an abstraction over an array. Yeah.
Is this just like what we like our we make a copy of whatever we want to read out of it, like that deduplicate, and then you can just overwrite.
So what you say is you make a copy of whatever you read into some other data structure.
And then you can just overwrite.
Override, but then the data you get from there, you have to now go and copy at the right position. Ultimately, you want a unit. You want the correct unit, right? You're expecting 15 bytes. The 15 bytes are going to be converted into a string. Okay. So you got the first 5 bytes. You put that into your little data structure. Now you're getting the next 10 bytes. You've got to remember to go and put these 10 bytes after the first 5. So you need some data structure, whether it's operating system provided, language provided, or you're defined, that keeps track of pointers. That has pointers to arrays. And that data structure is called in Java a byte buffer. That's, yeah.
So how would you know that, so this points keep confusing me, like how would you know that the system has already finished supposedly duplicate that byte buffer to another data structure to store for later use, such as using the reads.
Which is what you had to do in your assignment, that you have to duplicate the byte buffer.
Yes. How would you know when it's finished processing so that the other standard will actually rewrite in the byte buffer? Like,
so how do you know when you received all the bytes?
like, how would you know that when you receive another new byte buffer, they can rewritten that byte buffer after the previous one has already been duplicated to another data structure for processing?
Okay, so okay, I'm not sure I totally understand your question. So, and you're getting a little ahead, but let's see. What I'm saying right now is we need to keep track of how much was read, right? Or written, right? So that's the problem we're trying to solve. Let's solve that problem, and then we'll get to your question. So is your question the same as the question I just posed? So how do we sort of keep track of positions? How much was read by the system, right? So we want something with pointers, right? Whether this gets duplicated or not, that's another thing. Okay, that has to do with the fact that you already consumed it. You've already got what you wanted, but you're not ready to process it. There are two stages here. One is that you haven't gotten how much you expected. So let's get those 15 bytes that you expect. Now that you've got the 15 bytes, you're not ready to process it because you're going and giving it to some other thread. So that's what's happening with duplicate. You're saying, I got the 15 bytes, now I want to duplicate it, and new thread can deal with it. But right now I'm talking of a simpler problem, which is just waiting for the 15 bytes to be received. So I don't want to duplicate right now. Right? So that's the byte buffer. And what do you think? What kind of pointers do you think the byte buffer has or should have? Yeah.
Capacity,
Capacity would mean what?
like the amount of indices in the byte buffer.
Okay, the array. So it's associated with an array. Is the size of the array. Okay.
And then it would have like a current pointer.
Current
So
pointer.
where the data has either been read up to or written up to.
Okay.
Is there, I know there's like 3, but isn't it limit?
So we need at least 2. We need the size. We have the size, which is the array, and we need a position. So where we should, if it's being written, where the next byte should go to. Okay. And if it's being read, where to start or where to end? Maybe where to start too. That's why you need more than one pointer. Okay, so one position was not enough.
And length.
Size. That's what he's calling size. We need the size, and we need if you're writing, from what point to write onwards, and if you're reading, which portion to read, because you may not be reading till the end. Okay, you also may not know exactly how much will be received, so you want to know the first position and the last position. Yeah, somebody was raising the hand. Yeah.
It doesn't seem like you need a start and an end and the size. Like you should only need 2 of them, right? Because you can compute the third.
So why do you need start and size? Remember, the reader may not even know how many bytes are going to be sent. So it just allocates a big enough buffer, and then it may get. It says, I don't know, the message could be between 5 and 500 bytes. So I'll allocate 500 bytes. Now the question is,
So the end is in the 500 byte necessarily, because they might only start. Okay.
and you may use the same read buffer for all messages, multiple times. That's the duplicate thing. You got a message, you duplicated it, send it out to somebody, and then use the same buffer again. You could do that. Okay, so there's all these considerations. Okay, and and actually there's 4 pointers. Okay, so you need a storage. That's your array. You have to have the size. That's your capacity. So you have the position of next element to be read or written. That's the position. So read may not yield expected bytes. Okay, and write may not empty all the bytes. So we've got a limit. We've got another pointer. Okay, and I guess this is more than what I'm saying here. It's also saying that what you may get or write may not fill the buffer, or so may not be the full buffer. Okay, so what you may read may not be the full buffer, and when you write, you may not write the full buffer. So you need limit for that also. And then there's a notion of what has been consumed and not consumed. Okay, so this is tricky. And I had to use this in an IO manager, that I got the first 5 bytes. Okay, I'm expecting 10 more bytes. Okay, so I need to sort of so I being the system. Okay, when I get more, so there's the application layer, the system layer. Okay, somehow the system layer is expecting 15 bytes. How? Maybe the size was sent earlier. Okay. So the system has gone and filled 5 bytes, and it's expecting 10 more bytes. So it says, okay, I need to know where to write the 10 extra bytes. Now, the first 5 bytes have not been consumed by the application. Okay, so these 5 bytes have been read by me, the system, but not been consumed. So I want to mark the position that was being consumed. So when I finally get all the bytes, I tell the system, hey, this is the unconsumed portion. This is the portion you should look at. Okay. So we also have a mark. Okay. And that's sort of the first unconsumed position. Position is the first you know, yeah.
So if the application like wants to consume from the buffer, but like the system knows that it's still waiting on 10 more bytes, would it block?
So that's the thing. So that's the blocking issue. So right now, it could block or it could be notified later. It could keep trying. Okay. So yes, somehow the application has to be delayed, and we look into that, the blocking semantics. Okay. And even if it's not the system versus the application, even if it's just one program that's doing it all, forget me that I'm not an NIO manager for you guys. Assume that this is just one application. The application also has to know how much have I read and how much do I need to, when I do my processing, where should I do my processing from? So the application is also wearing two hats. One is just receiving data, and then it is processing data. So I've kind of confused you a little bit by saying that the system and the application. Assume it's just one application. But it's got two hats. One is what am I consuming, what am I reading, and what am I consuming. So it has to keep track of both things. Okay. So these are the pointers. Okay. And the constraints are that mark is less than or equal to position. Okay. What you've consumed is less than or equal to what you've seen, and which is less than or equal to the limit, which is the end of the consumption of production, and which is less than or equal to capacity. Yeah.
If you're, so I want to ask a question about the sparing of the object. So if the object's bigger than what you can send,
Yeah.
will it also have like the position limit, or is it handled by?
So if the object, let's go and look at this. If the byte buffer is smaller than what the application wants to send, see, the application is going to give the system a byte buffer. Okay. So the system's concerned, that's all you have. If there was more data, you should have created 2 byte buffers, or you should have used a different byte buffer. The byte buffer was allocated by the application, not by the system.
Okay.
When sending.
So it's handled. So the system just handling. It doesn't matter. Like.
Yeah. And even when reading, in my system, I create the byte buffer. But if there was no layer, the application says, here's my byte buffer. And indeed, if the number of bytes that has been received is more than what the byte buffer is, the system will just fill up as much as it can, and then leave the rest for the next read. So this has become tricky. We are talking of stream communication, and yet we are, which is sort of a continuous thing, and yet we are reading and writing in chunks. Okay, and so that's why it gets confusing. Okay. Questions? Okay, so we've got the concepts. Let's just get the API. We've got the byte buffer API. We've got the byte buffer concept also. Okay, and the API, you can gather from that. There's a limit method and there's a position method and so forth. We know that there are 2 kinds of channels. There is the channel endpoints that we see on the top. They're paired up. And then there's a special kind of channel, which is this listener channel or a factory channel, which is like the usher in a restaurant I talked about last time, which just goes and gets messages to create private channels. Right? And so let's just go and translate these abstract objects into NIO objects. So the channel, what I'm calling channel there on the top is what data type in Java NIO? Yeah. Socket channel. And what is the server channel factory that I'm calling? Server socket channel. Okay. So they're both subclasses or subtypes of something called selectable channel. Okay. There's a server socket channel and socket channel. And why it's called selectable, we'll see later. And they are not totally foreign things from what you guys have used in your 431. You use Python, but had you used Java, you would have used the server socket and socket objects. Okay, and these objects have handles to these objects. Okay, so if you just want to deal with sockets and server sockets, you can use those abstractions, or you can deal with the NIO layer, which is more general. Okay, so you can get the socket object from the socket channel object, and the way you deal with sockets is you've got a get input stream and get output stream, and you then do stream operations on them, because you don't go and use byte buffers there. Okay, you're just using stream operations, and you either get an input stream or an output stream. In Java, they never implemented an input output stream, right? Anybody seen that? Yeah.
Talking about the stream API they added in Java 8.
So did they add an input output stream? No, the stream API, this stream I'm talking about has existed from Java 1.0. Okay, it's not the stream operations that you're talking about, the functional operations.
Yeah,
No, I'm talking about just streams in general. Okay, so you know how you can have system.in is using an input stream underneath. System.out is using an output stream. So when people motivated multiple inheritance a long time ago, the classic example of something that's both an input stream and an output stream. And they would say, we already have an input stream, we already have an output stream, why can't I have a subclass that inherits from both? Okay, and if you don't have such subclassing, you just duplicate the methods. So I'm just curious whether Java ever added an input output stream. I believe not. Okay, but Java keeps changing, and I can't keep track of it. So with sockets, you either do input or output. With channels, you can do input and output in the same channel object, and you do it in terms of byte buffers. Okay, so that's a big difference. Okay, so you can read a byte buffer, you can write a byte buffer. Okay, you don't have to get input stream or get output stream. And the way you get these channels is that you basically invoke a factory method, if you will. Okay, so you're not saying new server socket channel or new socket channel. You just say server socket channel dot open, and some class is used which you don't know about. And similarly, socket channel dot open, and some classes used about which you don't know. Okay, that's just the API. I mean, the concept we've seen earlier. Okay? But just to make this concrete. And the accept operation is done on the server socket channel, and the connect operation is done on which channel? Socket channel. Okay. So that's the API. Okay. Questions? You didn't use it directly, but it's there underneath. Okay, that's what your traces are showing you. The user. Okay, so we are going towards non-blocking. We're taking our time. We first looked at all the system concepts, like interrupts and so forth, and we looked at, and we went there from I/O. Then we've seen how IPC can be cast as an I/O problem, a more complicated I/O problem where we needed the accept operation, the connect operation, we needed even byte buffers. And now let's get into blocking issues. Okay. So